Hi everyone, so it's me Jay. So I am going to give you another discussion not in this video. So I will be going to discuss one of the most important and basic topic in differential equation, that is first order nonlinear differential equation. But before anything else, let's have a recap or a review of linear differential equation. So by the way, what is linear differential equation and how would you describe linear DE? Okay, from our previous lesson, we already knew that a linear DE can be expressed into this form. We have dy dx plus pxy is equal to qx. Okay, then this linear D is in the first degree since we only have first derivative, that is y prime, and it is also called linear since it resembles to the general linear equation of a line, that is y is equal to mx plus b. Okay, however guys, in differential equation we will not always be dealing with linear differential equation, but there are also equations that are non-linear in nature. So these equations, such as exact equation, we have homogeneous equation, and we also have Bernoulli's equation. So all those equations that I mentioned in first order have their own approach, have their own method no, in determining their respective general solution and particular solution. But in this video, I will only be going to discuss about Bernoulli's equation. Okay, so Bernoulli's equation. So let's first define Bernoulli's equation and the concept behind Bernoulli's equation. So we can actually say that equation is a Bernoulli's equation we if it follows this form. Now we have dy dx plus pxy is equal to the function of x y raised to n. So it is quite similar with linear form. However, the only difference is that it has a variable y raised to n at the rightmost of the equation. And n there is not equal to 0 or 1. Okay, so in solving for the DE for Bernoulli's differential equation, then we have to introduce a new variable, and that is v, where v is equivalent to y raised to n minus 1. So by introducing v, we can actually reduce the Bernoulli's equation to a linear equation. And then we follow the procedure for linear equation in determining the general solution. So basically, to sum it up, Bernoulli's equation, the procedure, it is just by converting the equation into a linear form. And then that's the time we can actually use a linear equation procedure in computing for the general solution and or particular solution. Okay, so how are you going to get to compute for those in linear equations? So it is done by introducing a integrating factor, or we have the mu x, right? So let's have a recap on our LDE. So that is our mu x is equivalent to 1 over, um, sorry, our mu x, the integrating factor, that is equals to the e raised to function of x dx. Okay, this is our integrating factor. Integrating factor. Okay, so let's try to solve a problem now in Bernoulli's equation. Okay, we have this problem, this DE. We have 6y prime minus 2y is equal to xy raised to the fourth. But upon looking at the equation, we can easily identify that it is a Bernoulli's equation. Why? Since it has y raised to the fourth at the right side of the equation, correct? So it is y raised to the n, where our n at this side is equal to 4, correct? So how are we going to get the general solution? First, we have to eliminate y raised to the fourth at the right side of the equation. So by dividing both sides of the equation by y to the fourth, or by multiplying the both sides of the equation by y over y raised to the fourth. So it is then that's by 6y prime minus 2y is equal to x y raised to the fourth. So multiply this by 1 over y raised to the fourth. Okay, so distribute 1 over y raised to the fourth inside the bracket. Then we can say that is 6 y negative 4 y prime minus 2 y negative 3 is equal to x. Okay, then after that, introduce a new variable, that is v. Okay. Introduce a new variable v is equal to negative 2y raised to negative 3, and get the derivative dv is equal to 6y raised to negative 4 dy. So we can tell that in this equation we can say that it is the that is our dv, and this is our v. So we can now eliminate all the variable y and change it into or substitute it by introducing a variable v. So then we can now express our equation into, we have dv is our dv plus we have our v is equal to x. So this is now our linear differential equation. Why is it so? Because it can express, it satisfies the general form dy dx plus ex y is equal to qx. But in this case, we are actually using v instead of y, because again, we eliminated all the variable y and change it into a single variable v. Okay, so in this case, our px is equal to 1, since we have 1, or we have coefficient of 1 at this side, and then our qx is equal to x alone. Okay, so by integrating or by in computing for the general solution of a linear equation, then we have to we have first compute for our integrating factor, which is our mu x. Mu x is equivalent to e raised to the function of x dx. Okay, now we have our mu x is equal to e. Now we have our function of x is equal to 1, and this is now 1 dx, correct? So our mu x here is equal to ex, correct? So therefore, our general solution, now we can use mu x now in computing for our general solution. Now the general solution of a linear equation is equivalent to, we have y is equal to 1 over our mu x, then bracket, then the integration of this is our mu x, then our qx dx plus c. Okay, however, in this case we are using v. Okay, so v 1 over e raised to x, bracket, we have the integration of e raised to x. Now our qx here is x, then dx plus c. Okay, however, we have a problem here. Ex dx, no, we cannot directly integrate it using the basic integration rule. So what we're going to do here is integrate it using by parts. Okay, so we now use by parts in solving the integration of ex dx. So we have the integration of ex x dx. That is, from rule of by parts, we have integration of u dv. Okay, sorry, that is integration of u dv is actually equal to u v minus integration of v du. In this case, our u is equal to x, our du is equal to dx, and our dv is equal to ex dx, then our v is equal to ex. Then substitute all the value of u, v, du, and dv in the by parts. So that is equal to the integration of ex x dx is equal to, we have our u, x, our v, ex minus our u, that is x, du is, um, sorry, our u here is equivalent to, okay, our u that is, sorry, that's our v. Our v is equal to ex, then du is dx. So therefore we can say that it is x ex minus ex plus c. Then substitute this in our general form, that is v is equal to 1 over ex, then the bracket, then we have the integration of ex x dx computed using by parts, that is x ex minus e raised to x, then we have plus c. Okay, so distribute the 1 over ex inside the bracket. That is what we have, v is equal to, then we can cancel out ex, right? So the remaining variable is x alone here, correct? Then minus 1 over ex times negative ex is equal to negative 1. That's plus c over e raised to the x. Okay, but in this but it doesn't stop there. Okay, we need to bring back y variable in the equation. So how are we going to do that? We know that our v here is equivalent to negative 2y raised to negative 3, if you remember. Okay, so we have bring back y, no, substitute negative 2y, negative 3 in variable v, then we can say that it's negative 2y is to negative 3 is equal to, that is x minus 1 plus, or let's bring ex to the numerator, then its exponent will change into negative sign, that is c e raised to negative x. So bring negative 2 down equation, divide both sides by negative 2, then we can say that negative 3 is equal to x over negative 2 plus 1 half plus, or that is ce negative x over negative 2. Okay, so we have y is raised to negative 3 is equal to x over negative 2 plus 1 half. However, we know that c over negative 2 is equivalent to c, correct? So it's still the same as constant. When we multiply or divide a number to a constant, the result would still become a constant. The result is c raised times e raised to negative x. This is the general solution of the differential equation.